National Study Committee C1 on Power System Development and Economics. Ladies and gentlemen, we are honored to have with us Mr. Santanu Sen, representative of SIGRE National Study Committee C1 on Power System Development and Economics and General Manager CSC Limited. Sir, we are really grateful to you for your gracious presence and also thankful that you took time from your busy schedule for this session. Ladies and gentlemen, this tutorial is planned for 90 minutes, that is 1.5 hours, where the query session, that is the Q&A session, shall be taken after the end of the presentation. For this tutorial, we have with us the eminent speaker, Mr. Yuri Simberg from Canada. Sir, we are obliged that you agreed to our request for taking this tutorial. May I now request respected Shri Santanu Sen sir to kindly enlighten the participants with his vast experience on the subject of tutorial. Santanu sir, over to you.
Thank you, Shashank. Can you hear me, Shashank?
Yes, sir, you are audible.
Yes, thank you. Thank you for giving me the opportunity to talk to you all. So I am Shantanu Sen. I am working with CESC Limited, Calcutta Electric Supply originally. We are the oldest utility in India. We are more than 120 years old, but we are smart utility also. We are doing good in city of Kolkata. So I have worked in the field of protection, automation, metering, condition monitoring, and GIS field. Now I am placed in planning department. So what I see that as distribution engineer, electrical business, the distribution utility business has become more and more challenging day by day. While utilities are striving to improve their operational parameters continuously, there is constant pressure of reduction in cost. So we have to improve the SAIDI figures, improve in the loss figures, but cost, the operational cost and the capex has to be low throughout the tenure, and the assets are going bad, going aged. So in that area, uh, what I felt that utilities are always trying to adopt new technologies, innovative initiatives for the asset creation, automation, and maintenance process to enhance the customer happiness with improved performance parameters. So utilities are trying to become more good organization to excellent organization, and finally they are trying to become outstanding organization in the field of distribution of power. So I'll share a small experience with you. What we did in CSC, we had Singapore Power, our technical collaboration in the year 2008, almost 12 years back, when we found that they are doing condition-based monitoring of their plant and equipment, and we inducted that from their practices. So condition-based monitoring we have started long back, almost more than a decade back, and we are getting results out of that. And through this condition-based monitoring, what we found that we are doing some maintenance of big assets like gas insulated substation, transformers, outdoor ears, indoor switchboards. All assets are being monitored periodically through partial discharge measurement equipment or temperature measurement equipment. But we are also doing some IoT based real-time online condition-based monitoring of assets also, like contact temperature of busbar spout and circuit spout of 33 kV AIS boards, outdoor installation temperature measurement through pan tilt zoom camera, thermal camera, and also we are doing some good work with online partial discharge monitoring of underground cable. In city of Kolkata, we have many voltage level underground cable We have started monitoring 33 kV cable, underground cable, online partial discharge monitoring, and we have good results. So there are so many use cases for going ahead with so many condition monitoring approaches. The results are quite encouraging in CSC. We have reduced SID SIFI figure by a lot, by numbers, and also we have reduced the fault repairing cost. Fault repairing cost, as because we are doing condition based monitoring, so we are identifying the problem well in ahead before the flashover occurs. So we have reduced the damage as well as the reduce the repairing cost of the identified problem, removing the problem areas. And condition monitoring has helped the maintenance engineers life very easy, has made the maintenance engineers life easier. And with this COVID-19 situation, we felt that condition monitoring is more prevalent, more promising, as because we don't want to expose our maintenance people together working for identifying a problem, maintaining a problem, going for a transformer maintenance in this COVID situation. So if we send some few people and identify the issues, and if you have real-time monitoring, online monitoring with smart sensors and IoT, so that would become very easier for people going ahead, that more less people will be required for condition monitoring also in the field. Physical work will be limited. So SIGRE has published one document number 823, B3 Technical Brochure 823 reference December 2020, that talks about substation servicing and supervision using mobile devices and smart sensors. That's a beautiful book. All requesting all of you to go through that book. So its number is 823, substation servicing and supervising using mobile devices and smart sensing. So there are many research document as well as few use cases which you will like. I will not take much of your time. Best wishes to all of you. The eminent speaker will share his decades of experience working in this field. Thank you so much.
Thank you, Santanu sir, for your informative and educative address. Now, before we start the presentations for today's tutorial, I would like to introduce the protagonist of the program, that is Mr. Yuri Simberg. Mr. Yuri Simberg is a director of asset management with Kinetics Incorporation, which has been the leading corporate consulting services in asset management area. He has successfully completed many asset management projects across North America and Europe. Mr. Yuri also authored and co-authored many published papers in industry magazines and forums such as in SIGRE and IEEE. Prior to his joining Kinectrics, Mr. Yuri spent 30 years with Ontario Hydro and Hydro One. Mr. Yuri Simberg was Canadian representative and management team member as the asset management convener at SIGRE Study Committee 1, System Development and Economics. In 2018, he was awarded the prestigious SIGRE Technical Council Award in recognition of his outstanding contribution to SIGRE's work. Mr. Yuri is a convener of SIGRE's working group C1.43 requirements for asset analytics data platforms and tools in electric power systems. Ladies and gentlemen, these few words cannot justify the immense knowledge and experience Mr. Yuri has, but I assure you all that you are in good hands. Now, before requesting Mr. Yuri for his presentation, I would like to announce to all the participants to kindly keep yourself muted during the presentation. Mr. Yuri has decided that he'll be interacting with all of you in between the sessions. He'll be intimating about you about the interaction. And And before that, I'll request all of you to kindly please keep yourself muted to avoid any disturbance to the presenter. Now, moving further, I would like to invite Mr. Yuri Simberg with his presentation, please. Mr. Yuri, over to you.
Thank you very much. Guys, can you see the screen? Just want to make sure you see the presentation.
Yes, sir, we can see it.
Okay, well, thank you so much for inviting me, and thank you very much for a nice introduction. I'm excited to do this presentation. This is not my first experience dealing with Indian utilities. I was fortunate enough to spend a few days 2 years ago in Mumbai, where I was training Tata Power engineers in asset management, and it was a really good experience. So this is really nice for me to kind of go back to where I was before, and I look forward to spending some quality time with you guys. What I would ask you to do is I'll try to stop every few minutes and see if you have any questions. I don't want to keep all the questions to the end. I'd like to kind of have more interactive discussion as we go along. And hopefully, if we have enough time, I have a little demo of visualization of some of the asset condition assessment results. So let me start. And by the way, the first speaker, some of the points he made were very relevant, and I might defer to them during my presentation as well. So see if I can start moving things. For some reasons, it's not moving. Now we have to, okay, here's my, basically this is agenda for what I want to cover today. I'll tell you a little bit about Kinetics, which is a company I'm working for. I'll talk about component-based health indexing. I don't know the level of knowledge in asset management, so I will talk about some of the basic concepts, but I will also talk about some of the newest development in this area. So component-based health indexing, I'll talk about all asset condition assessment process. I'll talk about how to develop risk-based long-term strategy. I'll also discuss ISO 55000 standard. It's a standard for asset management, which has superseded, I don't know if you guys know, past 55 specification. That was a previous document. I'll talk a little bit about some ways of measuring performance. And one of the things that is happening now in the industry, a lot of utilities are trying to acquire or understand the needs for what's called asset performance management tool. That is a tool, IT tool that facilitates more efficient asset management. So I'll talk about this a little bit. And if we have time, I'll try to do health index visualization demo, just to show how you can manipulate the results to kind of understand what really areas of a system you need to worry about more. Okay, so let's get going. So a little bit about Kinetics, who we are, not too many slides. We're in Toronto, Canada, one of the largest consulting firms in Canada. We have a great campus. You see the picture. Those all are buildings. And in those buildings, we have 25 laboratories. We have a lot of business that we do in a nuclear area, but we also do quite a lot of business in transmission and distribution systems. In fact, we have business in India as we speak. We have a number of Indian technicians who will be in our campus being trained for running what we call Line View robot. It's a robot that checks condition of ACSR conductors on transmission lines. So we have kind of a, I would say, part of a company in India at this point. Just about 1,100 people. We've been in business for over 100 years because we started as part of Ontario Hydro. Those of you who are old enough probably remember Ontario Hydro was one of the biggest utilities in North America. And most of our staff are kind of experts in their respective fields. So we're known around the world. We lead a lot of committees, and so our knowledge is usually state of the art. So I'm really grateful to have this opportunity to share it with you guys. And I mentioned LineView. This is this little robot. See, it's here. I don't know if you guys see my pointer. It kind of runs along conductor and kind of indicates any areas along the span where you have. I hear some noises. Hello? I see some background noise. Is it possible to get everybody on mute, unless you have a question?
You mute them, sir, please.
Okay, I'll try it because it's I can hear somebody talking in the background. Okay, thank you very much. So we have many labs. We have obviously laboratory where we can do high voltage testing, high current testing, mechanical testing, where we can test conductors and other things. We can test underground cables. So the reason I'm saying those things, that what I share with you, it's really proven. It's not theoretical. We've done many projects with utilities, and then our background and support for our findings is really based on our hands-on knowledge of equipment. So I'm going to start with the basic concepts. I think I'm going to apologize if some of you are familiar with it, but I think it's probably not a bad idea just to go over what is health index. This is Kinetics' approach to health index. It's really it looks like real strange formula, but what it is, and I'll show you an example which makes it simpler. It's really a means of quantifying condition of assets. It's not good enough in making decisions just to say this transformer is in better condition of this transformer, but not in as good condition of that transformer. What really helps, you can say score of a condition of this transformer is X, and score of a condition of that transformer is Y. So if X is higher than Y, it means that this transformer is better than that transformer. So how do we get to those quantifiable numbers to assess condition? This is where we use a formula. It has two tiers. First is a top tier. We call it's a health index. And in numerator, you have product of what we call condition parameter scores multiplied by weight of those condition parameter scores. The weight kind of symbolize how important the condition parameter score is in indicating end of life of that particular asset. And it's normalized over the best score possible. So the range for health index is from 0, which is a horrible asset, to 100, which is a brand new asset. The DR stands for the rating factor. This is to allow us to, in some areas, all things being equal, you might know this transformer, for example, is exposed to high number of through faults. So we will derate condition of that transformer. Or this particular section of a line is close to C, so there's excessive corrosion affecting conductor, so we'll derate that. Some of those condition parameter scores, and I'll give you an example in a minute, are not very straightforward. There are some mini health indices, so we have similar approach in calculating condition parameter scores using subcondition parameters. So this is why we have two tiers. And I think it's a little bit confusing, but I want to take you to the next slide. And this is an example of health index for transformers in a more simplified terms. So this box in the middle is your top tier. It's a health index. And transformers are fairly complicated. It's probably the most complicated asset in transmission distribution system. It has a number of components. It has insulating oil, winding, insulation, bushing, arresters, etc. I think there are about 10 different components. So this is what you see at the top tier. Each of those components is a parameter. For each of those components, we will calculate a score. And score for each of the components is on the range from 0 to 4. How the scores are calculated? So now we're going to second tier. So for insulating oil, this is what you do to calculate condition of insulating oil. You look at results of dissolved gas analysis. You look at results of oil quality testing. Look at the results of oxygen inhibitor. I'm going to pick arbitrarily something else. Let's say you look at pumps. So you look at oil pumps bearings condition. You want to look at arresters. So that is, you look at relays, gauges, and control box. Obviously, none of the utilities we work with, and if I ask you guys listening in, you won't have all the data that's needed, which is okay. There's some parameters that are more important than others. So as long as you have those, you can have a health index developed. Keeping in mind that the more input data you have, the more reliable is the input data, the more is the credibility, the higher is the credibility of your calculated health index score. So what I want to do, I want to stop at this point. Any questions? So can I proceed? No questions, guys? Kind of familiar with this concept? Okay, so I'll keep going. I think yeah, go ahead.
I have a question here. So, do you also measure the winding temperature
We use whatever information you have. If you have winding, well, again, winding temperature will change depending on the loading, right?
Yeah.
So
That's why
what?
actually
Yeah,
that is important
yeah,
for
it's very,
determining the
yeah, yeah. So one of the things we would do is we would look at kind of a loading history of that transformer, how it was loaded. And depending on
Okay.
availability of data, one of the things is, some utilities don't have, real-time loading information, which is a lot. So we would ask them, give us 5 years of monthly picks.
Okay.
And then we compare what we get from those calculations with your nameplate rating for what transformer. They also, what we can include if you have this knowledge is number of instances when it was overloaded, right? Because you can withstand limited time rating for a certain period of time. So if you have that information, it shortens your life. Although if you stay within prescribed limits of overrating, you won't shorten your life. So if you have this information, which very few have, it will be used. But a very good question. Yes, loading is important. And I think I'm going to give you another example where it's really important. So if you look at two transformers, one, for example, installed in Kolkata in the south of India, where it's very hot, and your peak load, I assume, would be in the summertime. So the transformer will be stressed the most during summer because when its ambient temperature is high and load is high, it's not good. You take the same transformer, you put it in Canada, where in many places it's winter peaking utility. So when you have the highest load, your ambient temperature is pretty cold. So I can guarantee you that transformer in Canada will last longer than transformer in India.
Yep.
Okay, did I answer your question?
Yeah, that answers my question.
Okay, any more questions?
Hey Yuri, can I ask?
Yeah, of course.
Yeah, I have a query. If after all these calculations on different components and weightages, we come to a number which is some number in 0 to 100, and then how do I? Because ultimately the importance of this number is getting the health index and deciding whether I have to go for maintenance or replacement of the equipment altogether because it is going to fail. So whether maintenance is required or whether it is going to fail and I need replacement, how do you come to that number? That this number is a threshold, and do you use the statistics or your past failure data of different utilities and then benchmark it and then use it to use that model, that machine learned model to the other utilities, or you uh, 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 is there any other way also to determine the thresholds?
Okay, very good question. I think so. One thing needs to be understood. What you have health index, the score from 0 to 100, is not telling you what you need to do when and how. The purpose of health indexing when you do this is, and I remember the speaker before mentioned that you have limited resources, so you have to decide where to spend your money. So the purpose of health index is you have a population of so many units, transformers, breakers, whatever it may be. The purpose of health index is to focus on a sample or subset of that fleet that requires some action. And then you go to the next stage. What is exactly the action that you need to do? And I'll talk about it later in the presentation. Do you want to replace it? Do you want to refurbish it? Do you want to repair it? Do you want to do nothing? It would depend on specific circumstances. So what I'm describing here is just the first step. It's not the end game. The end game is exactly what you said. The end game starting with units that identify to be poor and very poor and decide what is the appropriate action in dealing with those units. Did I answer your question?
Okay, thank you, Yuri.
And we'll talk a little bit more how to make those decisions later in the presentation, okay? Any more questions? Okay, I'll keep going. So as I said, that was actually a good connection to the next area. This is the first step in the process. This is not the end of the process. This is the first step. It gives you an idea what your numerical representation of condition is. And I want to mention something else. This is indication of long-term degradation. You're going to have some small failures along the line of your assets. It doesn't mean you have to replace it or rebuild it. When you look at health index, it's an indicator of end of life, how close you are to the end of life. The lower the score, the closer you are to the end of life of that assets. So the total asset condition assessment process actually has three main components. The first one I just described is health indexing, when you quantify condition of your asset. The next one is risk assessment. And Risk assessment really has two components. I always ask the question, what's the difference between risk and consequence? And a lot of people don't know the difference. But there's a big fundamental difference. Risk is a product of two things. Risk is a product of probability of failure times consequence. So you can have very high consequence, but the probability of failure is not very high. Your risk is not very high. And what drives probability of failure is condition of your units. So the worse the condition, the highest probability of failure. The consequence will be exactly the same. Whether it's a new unit if it fails, or a unit in a poor condition if it fails, the consequence will not change. But the probability is really related to condition. So I'll talk a little bit about that. And once you establish how you approach your risk, and the reason it's important to include risk in assessment is you may have two transformers, one in downtown or important area of the city, for example, and one somewhere feeding a small village. They're not equally important. The one that, for example, serves more customers is more important. So when it fails, more customer will be impacted. So this is difference in consequences. So if you look at two transformers in similar condition, one, if it fails, will result in outage for many more customers, and one will result in outage to fewer customers. So obviously the one with failure that will impact more customers is more important in the sense that it has to be dealt with sooner rather than the other one, okay? So that's what risk-based approach is. And based on risk approach, one of the challenges many utilities had historically, and some still do, is that they don't have long-term plans. I mean, it's you have money and then all of a sudden things come up and you have to spend all the money this year, or you won't have enough money for next year. So one of the benefits of asset condition assessment is that you develop long-term plan. You look for maybe 10 years in the future based on what you know today. It might change, but based on what you know today, those are your plans for units that you need to address. And when I say address, not necessarily replace. That is why we don't call it replacement plan. We call it flagged for action plan, because your action could be, as we talked about it, it could be modified maintenance. You can move from time-based maintenance to condition-based maintenance, for example. It could be refurbishment. You can replace a bushing on your transformer and you get a few more years of a transformer, for example. It could be major refurbishment when you want to flush oil or rewind, winding on a transformer. That's refurbishment. Or you may decide, I'm not going to do anything. So those are the things that are the actions. And depending what type of action it is, it may be capital in nature, and it could be maintenance in nature. But the first step in deciding for which units you have to make this decision comes with risk assessment. Okay. One of the things that's important to remember, and asset management, when you use formulas and you show this big formula, it's not deterministic formula. It's probabilistic formula. The whole approach to asset management is probabilistic. And probabilistic means you're going to be wrong most of the time. So the question is how wrong you're going to be. So one of the things we found, that's a new development in asset management, how you approach health indexing is you can have a pretty old unit that seem to be in pretty good shape based on health index. So you have transformer, which let's say is 65 years old. But it looks like, based on the health indexing formula, looks like brand new unit. Well, you know that there's no way it's going to last another 65 years or 60 years. So what we agreed with, and that's actually worked out very well with some of the utilities, we impose age limiter. So given age of a unit, you can only get a certain maximum score. You can, for example, on this graph, if you're 60-year-old unit, and if you move up, you cannot be better than, for example, 40% score in this case. I mean, it's not a really good curve, but the idea is if you calculated your score and it happens to be below your age limiter, that's the score you keep. If you calculate your score and it happens to be higher than the age limiter, then you bring it down to age limiter. And that really is a very reasonable approach to take into account that age is not equal to condition, but nevertheless, there is some impact of aging that you can't capture necessarily. As sophisticated your health index may be, you still may not be able to capture it. So that accounts for that. I would look at it as an example, if you're a 60-year-old man, you can be in fantastic health condition, but you'll never be as good condition as 19-year-old guy. Okay? You may be in maybe 40-year-old condition, but not 19-year-old. So you have to impose some limit to have some reality. Now, this is also very important. And one of the ways of deriving your degradation curve, which is an indicator where you are, what's your probability of failure, is to have a record of your removal statistics. It's not very difficult, and many utilities, unfortunately, don't do that. All you need to record is age at which units were replaced or removed. Ideally, you'd have a cause of removal. And if causes failure, or it causes because you replaced it, it was about to fail, that's a condition-based replacement. So that will be a failure curve. If it's removal for other reasons, for example, you're expanding your roads, so you have to move something or replace something, that's a removal statistics. It's not as good as failure statistics, but it's not bad. So whether it's removal statistics or failure statistics, you should be able to generate this red curve. What it says basically is for this asset category, as an example, most of the units will be replaced in the age range between those dotted lines. This red curve, it's called probability density function. And from probability density function, you can derive, and it's very specific direct calculations, you can derive the other two curves. The blue curve, which is, it's called actually probability of failure, which is cumulative probability of failure. What it means is at certain age, what's the probability you will fail? And obviously, the higher the age, the higher the probability of failure. And your degradation curve is 1 minus this curve. Its survival is 1 minus probability of failure. The other curve, this one here, is your rate of failure. What it means is if you're a certain age, what's the probability you're going to fail that year? So they're somewhat different things. And really, this curve, the cumulative curve, is really integral of this rate of failure curve. So those are things that are very important in relating condition to probability of failure. And I urge many utilities to start collecting this data. You don't need a huge amount of points to be able to do that, but it's very powerful because the degradation curve is unique to your utility. Even within India, you will have different degradation curve for different utilities. And so if you start using degradation curves, Sigrid has degradation curves generated by different studies, by different communities, but they are kind of industry curves. They are okay, generally speaking, but if you use industry curves, they do not necessarily represent your local circumstances. So you have to, if you can, generate your own curves. If you don't have statistics to generate your own degradation curve, there's another methodology. I'll touch on it briefly that we use. You need to understand what the 2 points are on for your useful life of your assets. The first point is pretty straightforward. How old is your oldest units? So if you have demographics, if you know age of your oldest breaker, or SF6 breaker, for example, and that's your point. And you can assume that at that point, your probability of failure is close to 100%, maybe 95%. So that's easy. The second point is a little bit more difficult. We define it as a typical useful life point. We call it actually 80% survival point. What it means is if you install 100 units, at what point in time 80 would still be in service? We've done this exercise probably with a couple of dozen utilities, and all of them had a pretty good idea what this point is. This is where your units start failing, start experiencing problems. Because most of your failures actually occur between this point and the point where the oldest unit is. Having those 2 points established, having ages for those 2 points established, and associated probabilities also allows us to generate degradation curve. It's not as accurate, it's not as credible as the degradation curve based on actually failure statistics, but if you have nothing better, then that's something that could be used, and going forward, you'll maybe replace it with the real curve. The other part of your risk equation is criticality. Criticality is a measure of impact. So what happens when something fails? Usually there are 2 types of impacts. One is local, that's physical impact, impact to safety of employees and public, how many customers may be impacted is already system impact. So they're different. Number of customers impacted, system impact, maybe the connections being impacted, your impact on protection and other things, that's your system impact. So really it's a combination of 2. System impact and local physical impact. Just want to show example of criticality matrix. Again, it's what I'm showing you as example is for transformer. So first is load criticality. How is critical load that transformer supplies? And it describes what it meant by that. And it also weight, because not all criticality factors are equal. It looks similar to health index, but it's really not, because health index is more rigorous. The calculations for health index scores are based on test results, inspection records, loading, as we talked about, etc. This is more of something where gives you choice as utility professionals to decide, okay, what's a low criticality? You can say, well, if I have X customers impacted, it will be high. If you have fewer than X customers, it will be low. In some cases, when we have criticality matrix developed, we actually have high, medium, and low. I wouldn't go more than that, because the idea is to establish relative criticality of assets. Still, the major driver for decision making is condition, but for units in similar condition, then you go to criticality. So next thing is physical protection. It describes what it is. Customer impact, so how many customers, because you can have few customers but very high loads, or you can have many customers but not necessarily high loads. So you can look at both those considerations. Location has to do with physical protection. System impact, it's usually for bulk system units, not for load serving as much. It's for auto transformers, for example, for major transmission lines where if you lose it, there's no load loss necessarily, but it has a significant impact on your system performance. Short circuit exposure, etc., because you might have delay clearing, so it's going to take you longer to clear a fault, so that makes this unit more critical. I'm not going to go into detail this formula because I want to go through and have some more questions maybe answered. But you can calculate a criticality score, and combination of those two things gives you risk score. But I want to now get to this slide, and somebody asked me a question, like, have the score from 0 to 100. What does it mean? This is kind of interpretation of what it may mean. If you look at a transformer and you get a certain score of a transformer, and the problem with transformer, you're not going to say just, this transformer is 35%. I want to replace it. I want to do something. No, in order to make a right decision of what to do, you need to look at what made it that score, what made it not so good. So you have to go down to component level. And once you look at a component level, it sometimes drives you towards making a decision of what to do. Fundamentally, the three possibilities. The one is something small happened. You have crack bushing, you have leaking gaskets. It's something that may cause failure very quickly, but it's really not a cost to replace the whole transformer. All you have to do is make small maintenance fix, and you can get another 20 years of service from that unit. The second problem that made the score low could be actually long-term degradation, where let's say your paper is not good anymore. You can flush your oil, but it doesn't matter. 6 months later, you still have high ppms, and if you do paper testing, you're going to have some issues. So that tells you that the unit is at the end of life. The question then becomes, when is the right time to replace it? Do you want to do it this year? Do you want to do it next year? So there's some economic assessment that needs to be done, where you look at cost of incremental maintenance as opposed to savings from deferring replacement. And based on a comparison of those two things, you make a decision what makes more sense. So that's two options, but there's a third one where, based on test results, based on things that you get, that something is not right with your transformer, but you don't know exactly what it is. So in those cases, it makes sense, rather than just jump to a conclusion, not having all the facts, is to perhaps schedule some specific targeted testing. You don't do it for all the units all the time as part of your maintenance program, but for units when you have to make a decision, it may make sense to maybe spend a little money on some targeted testing to avoid replacing transformer you don't really have to replace. And in terms of messaging, that's another thing. That's something that can help utilities and decide what to do. When you get your health index score, and this is really brand new stuff we're developing right now, there are really two factors you look at. There's historical accumulation, long-term degradation, so something that keeps happening over and over again. You have, for example, a rate of dissolved gas analysis, the numbers historically rate is going up because it's not just absolute number you look at rate of change. So there's no danger of imminent failure, but you fundamentally know you're close to the end of life, so you need to plan for replacement refurbishment. It might require some lead time, it might require some spares to be ready, or whatever it may be, but it's time to start making plans to do something drastic. You can start adjusting your maintenance practices, but it'll buy you maybe some time. And again, you have to make an economic decision. Does it make sense to spend more money on maintenance to buy a few more years before replacing it or not? The next one is latest findings. So what we just found. So the first part, when I say historical, it really addresses a capital need, when you need to spend capital money to replace things, and can you use some maintenance things to maybe delay when you need to spend the money. The next one really addresses you finding something that needs to be dealt with right away if you want to keep it in service. So if you have a car and your brake pads on a car worn out, your brakes don't work, it doesn't mean you have to buy a new car, but you have to replace your brakes very quickly. So if you take it to garage, you take it to mechanic, and they find that you have to do something very quickly, you have to do it very quickly. So that's based on the latest finding. You might not have the problem with the brakes over the years, but now you have it, and you have to fix it. Any questions? I want to stop here for a minute. Any questions? Don't be shy. Okay, I'll keep going. Yeah, go ahead.
Sir, can you share that PDOF curve again, probability curve?
This one?
Yeah, this one.
Okay.
So I got that dark blue curve, what it is, and the gray curve, what it is. I could not follow the red curve, the Weibull function.
The red curve is what's called probability density. It tells you how many units fail at what age. And this is really the curve that you use to get the other two. That's your starting curve.
Okay, thank you.
Okay. Any more questions? Okay, so we talked about the importance, one of the benefits, one of the things that asset management is very powerful at helping is in developing long-term strategy. And the different approaches to how you apply this strategy. So there's some units, especially on the distribution side. I assume some of you are working for distribution utility, and you have many small components. You have pad-mounted transformers, you have pole-mounted transformers, perhaps you have distribution poles. Those things you don't really maintain very much, and when they fail, you replace them. There's nothing wrong with it. It doesn't make sense economically to spend huge amounts of money on doing preventative maintenance, because when they fail, the consequence of failure is not significant. So for those units, when you develop long-term action plans, all you want to do is have an idea of how many units you expect to fail every year. And very often, all information you have for those units is age, how old those units are. So what you do is you have your age distribution, you have demographics, and you have a degradation curve if you have good statistics. And if you don't have good statistics, you can use the other methodology I talked about. And from that, you can estimate how many units you expect to fail each year for the next 10 years. You don't know exactly which specific units are going to fail. All you know is how many units are going to fail. So that allows you to plan for how many units you have to have in spare parts, and how many staff members you need to have if it happens. So this is what we call a reactive replacement. You run them to failure, if you heard that expression, and when they fail, you replace them on that time. For some other units, there could be bigger units, there could be smaller units. You don't have only age. You have some other information. You have some inspection records. You have some preventive maintenance records. So in those cases, what you do is you develop score for a specific unit, and you identify at what point in time you get to certain probability of failure when you need to have this unit replaced. You don't run them to failure. You replace them before they fail. But because they're probably not huge units, not big units, you don't really consider difference in criticality. You just treat them the same way. So your prioritization for addressing the problem is based on condition only. And finally, there's the third one where you consider both condition and criticality. Then in developing long-term plans for units that you need to address, you look at both. You look at combination of criticality and condition. So it will be a risk-based plan, flag for action plan. And then what it looks like. The blue ones is basically that's exactly the age when you need to do something. But if you take into consideration criticality, or if you decide to levelize things to avoid peak and valleys, then you can go to the orange one. So the idea is no utility wants to have peaks and valleys in the investments. They want to keep them as flat as possible. So when you use criticality to defer some investments, or when you use levelizing, when you say, well, this is what I think will happen, but no, I just want to levelize it. There's a means of levelizing. There's some forward averaging that you can do. And either way, this is really helping utilities in planning long term. Because when you go to senior management, they say, well, this is what we found based on the results of asset condition assessment. This is our forecast based on information that we have. So we have to have enough funds to address this many units in each of those categories. Now, and I want back to a question asked, okay, so how do you decide what's the right action? It's a really complicated diagram. I'm not going to go into all the details. I just want to describe to you a couple of things that you need to remember when you are doing economic assessment. It's only applicable, obviously, for units or assets that you don't run to failure. Because if you run them to failure, you just run them to failure, and when they fail, you replace them. But if you don't run them to failure, and you went through health indexing, and you found that there's some problems with some of the components, you know what those problems are, and you have to make a decision, do I replace it now, or do I do something else? It becomes an economic decision. The challenge with having an economic decision is that you know exactly how much it's going to cost you to replace, because you know your material and labor components of your replacement cost. You may know what would be the cost of incremental maintenance if you move from time-based maintenance to condition-based maintenance or to risk-based maintenance, that you have to maintain something more frequently and do maybe more intrusive testing to make sure it's not failing. You know what incremental costs may be because you do have unit costs for those. But what you don't know going forward, what would be unforeseen failures and what would be a repair cost associated with those unforeseen failures. So you have two unknowns in here. One is over the next so many years, how many and when you're going to have failures. And once you have those failures, how much is it going to cost you to fix them? So you can build uncertainty around timing, and you can build uncertainty around cost. And having those two uncertainties, what you can do, you can use Monte Carlo simulation to run it and see what would be the most optimal case. Does it make sense to replace it now? Or does it make sense to keep going using the results of Monte Carlo simulation for the unknown repairs? One more thing, and I'm going to stop for questions. Yeah, you had a question? Okay, let me do this. I just want to make sure, yeah. And I'll stop for questions because I'm almost finished with what I call equipment-focused asset management. This is a view of how you can prioritize your things. There are two ways of prioritizing. There's a way of prioritizing units within the same asset category. So you prioritize all the transformers. You prioritize all the breakers. You prioritize all the underground cables. You prioritize all the capacitors. And then there is a prioritization at a portfolio level. You have a portfolio of transformers you need to replace or address. You need portfolio of breakers, etc. So how to decide what's the right amount to be spent on which portfolio? This is kind of a high-level view. So remember we talked about health index for asset one, let's say transformers. You calculate probability of failure based on health index. You with criticalities, it's a consequence of failure. You develop risk score, and you develop this prioritized asset list of units that you need to worry about. You don't know the exact action at this point. This is what utilities decide, what's the appropriate action, based on the factors that I talked about, based on expected failures, based on economical consideration, etc. And that generates project list. That's for one style of assets. That's asset category. You do it for each asset category, no matter how many they have. And at some point, you need to use some methodology to prioritize between different investment categories to decide what's an optimal investment in all of them. It may be less than you need for transformers, but you'll need more for your wood pole structures, for example. So you have, and this methodology of an approach of prioritizing at a portfolio level is usually done based on impact on your corporate business values. What are those things? How are they important? And that will help you to prioritize and for whatever fixed amount of money that you have, either for capital or for maintenance, get the biggest results. I'm going to stop now. Any questions? No questions? Okay, so I'm changing gears a little bit. So far, we talked about equipment-focused stuff. I'm going to talk a little bit about more of a strategic stuff. I mentioned there's ISO 55000, and that's a standard. Many utilities are now trying to adopt it, which is a process where you have to understand what the utility has, what are the gaps, what are things you need to do to be eligible for certification. And there are 3 documents in ISO 55 series. I just want to take it, refer to a SIGRE technical brochure that we developed that was released, I think, at the end of 2019, TB 787. It's a translation of ISO 55000 specifically for utilities. And the key section in this brochure is section 2. It described 71 shells. Shell meaning you have to have that to be, if you want to be certified. And I'll address the 2 most important things of those shells, because some of the shells have the same things. Like in order to meet that particular requirement of ISO 55001, you need to have those things. Those 2 things that are most important are strategic asset management plan. And strategic asset management plan is basically a framework for decision making. It describes your policies, describes your strategies, describes your objectives. How do you decide when a portfolio management where to spend more money? It describes all the things, expenditure forecasting methodology. It shows your asset management KPIs, not corporate KPIs. A KPI stands for key performance indicator, or key performance index, whatever you want to call it. And how do you prioritize investments? So all those things that drive your decision making are supposed to be in a strategic asset management plan. And strategic asset management plan is common for all lines of business, for different asset categories. But for each asset category, you're supposed to have what's called asset management plan. That's specific to that asset category, and it has to have capex growth, renewal plan, operation of the maintenance plan, process improvement, and training and procurement and other things. So this is more of a detailed plan for a specific asset category, but the decision and the way things are in that plan are driven by strategic asset management plan. What is not well understood often are what asset management performance measures. So I just want to show that every corporation has vision and mission, and it has set of values. And driven by those things, they have policy and objectives. Every line of business have policy and objectives as well. And those policies, including asset management. And those policies and objectives could be the same as corporate, or it could be different, but have to be aligned. And one of the things you can have is asset management specific key performance indicator. So I want to give you an example of what those are. And also I want to give you an example of what is performance metrics. That's actually below KPI. It's more detailed assessment of how well you do your business. So examples of KPIs, your service quality. This is very reliability indices. Safety, 80, KD, Mayfi, their reliability. They measure interruptions. What is often not included are power quality. What are your sags and swells? How good is your voltages? Are they going up and down? And for some industries, it's extremely important. So that is something which is not well understood. So I'm giving an example of that. And interestingly enough, another part of your customer and performance is what customer thinks. What impact is on the bill? And are they happy with what's happening? And in many cases, if you conduct customer survey, there are two things that are very important to customers. One is how much they're paying, and two, what is reliability. But there are sometimes trade-offs, and some customers in some areas. I think it was surprising when I was with Tata a few years ago that in some areas our customers are actually willing to pay more to improve their reliability. Okay, so it's really specific. Cost efficiency. So, oops, sorry. Those are things that you look at the cost efficiency. How much of your labor costs are spent on supporting capital projects? How much are spent on supporting operational projects? What is your time management? You don't want to have a lot of overtime because overtime is not good. I mean, you should have plan enough to minimize your overtime. What is your productive time? Productive time means when you plan your activities, we call it sometimes wrench time. You have to kind of plan it so that they minimize your travel. So you really plan it so if you have to fix things, you don't fix it, come back, go to a different place. Try to fix all things in the same area. That's your productive time. And implementation of your plan. So are you spending money at the rate that will get you what you want, or you will run out of money when you get to the end? Are your costs, they have cost overruns? How's your schedule? All things are related. So if you typically run asset management projects well, you have to monitor your progress. If you get to the end and you're off, it's too late. So if you have something that you know you're off, you might try to make corrections as you go along. That's the purpose of this. And finally, this is more specific. How do you focus on parts of the system that need to be addressed? So percentage of feeders at rated capacity. That's a distribution one. Feeders exceeding planning capacity and the N-1 condition. Same goes for stations. There also, in many cases, unreliability is caused by subset of feeders. So if you address those feeders, if you fix problem with those feeders, and that maybe not that many, especially when it comes to underground cables, some of the specific areas of the system contribute disproportionate number of interruptions. If you address those, you might be fine. So you need to have those measures in place to be able to run the business more effectively. The last thing I want to show you here is what we call performance metrics. This is empirical thing of tracking whether your investments are made effectively, meaning that they achieve the results that they're supposed to achieve efficiently, what happens to costs, and accomplishments. Have you done what you set out to do? This matrix represents inputs into performance metrics. This is actually the matrix itself. So what is your corrective maintenance cost per mile, for example? What is your cost per wood pole test? Those are all measures, very specific, low level and KPIs, but still very important. And in this case, we're doing distribution lines performance metrics. What is your cost for foot patrol when you patrol your line? This is interesting one here. CM versus PM ratio. So CM stands for corrective maintenance, and PM stands for preventive maintenance. So the idea of preventive maintenance when you do foot patrols, when you fix things, is that you don't have unexpected failures. Because when you have unexpected failures, you have to send people in the middle of the night to fix them. Usually cost is higher. So the whole purpose of preventive maintenance is to minimize corrective. So if it doesn't happen, if you continue doing preventive maintenance and still have significant corrective maintenance cost, it would tell me that your preventive maintenance is not very effective. So you have to change things, how you do them. How do you know? Well, if you have number of years of data with this information, you can see immediately where the problems are and what doesn't make sense, and then you pinpoint what the problem is. This is a very powerful tool. You could be done for overhead lines, underground lines, stations. You could be done for vegetation management too, for example, so you know where they have the right cycles. It could be done for underground system. But this is a very powerful tool in assessing how well you run your business. Any questions? I'm going to talk now about APM. Okay, no questions. I'll go to the next thing. So what is APM? APM stands for Asset Management System. And you can appreciate, so when you do asset condition assessment, the stuff I described earlier, it's pretty intensive exercise. You need to get all the data you have. And this data could be from static sources where, you do periodic testing, periodic inspections. It could be from continuous sources like real-time sources, could be from monitoring equipment. You have to extract them, you have to combine them, and you have to then go through asset management analytics, which is pretty laborious and intensive exercise. So there's a platform called APM that does all those things, and I'll show you exactly what it may do, but this is where it belongs in your enterprise infrastructure. It links with your enterprise asset management system. This is AIP. This is your long-term capital planning system. It has data exchange, and it's really something that has a two-way communication link and is built on data. So more detailed description of APM is here. So this is the APM. What goes in APM are advanced metering infrastructure, if you have smart meters, GIS, some standalone databases, information from SCADA, information from the distribution management system, outage management system, monitoring information, if you have anything from RTUs or any of those things. So basically, this is kind of a spider in a web. It gets all this information. It has built-in analytics. So it can generate health indices, it can generate probability of failure, it can generate all those things. So it's done automatically. So you come into work today, and what you have in front of you is state of your assets as of yesterday, based on those inputs combined. If you don't have that, you can still do it, but you cannot necessarily incorporate your real-time stuff, and it's pretty intense information to do it manually. You have to generate all the outputs from different systems, combine them, and pivot it around the ID of your equipment, etc. So it becomes pretty intense exercise. Now, for APM functionality, it has certain features, have certain capabilities. So it should be able to deal not only with static data, which is what I talked about, periodic data, but also real data. And you should have ability to have used prescribed algorithms, like what I showed the formulas. You should be able to use that. You should be able to generate outputs that are helpful to you as asset managers, like dashboards, reports, emails, etc. And once you accumulate enough data, you should be able to start doing machine learning. You should start seeing trends. You should say, well, is this manufacturer is problematic in this area of my system when I have issues? So it's a very powerful tool. We're doing work now at SIGRE to define what specific needs are, and I'm a convener of the working group C143. We're kind of hoping to finish and issue technical brochure by the end of this year. And in that technical brochure, we're defining what decisions APM supports. We identify systems that APMs are linked with. We defined what are the functional requirements for APM as well as IT requirements. And we also define inputs and outputs. So we've just completed a survey of number of utilities addressing exactly those points. And there's some interesting results in the survey, and it will be included in the technical brochure. That's all. I want to now answer some of the questions, because I want to move into a demo showing how you can play with results of asset condition assessments. Any questions? I take it as no questions, right? Okay, I'll try to run a demo. You have to tell me if you can see it. I'm going to change.
Hello, sir.
Yeah, go ahead.
Yes, good evening, sir. I'm Rohini from CBSE office. There is one question in chat box from Mr. Sanjay Sharma that when we say a particular transformer has served 60 years, we may not get full picture if we do not its do not knowing its loading pattern through the years. So,
Right.
do you use any concept that takes this aspect into account?
So what you're saying is it possible? I just want to make sure I understand your question. Yeah, you're asking whether it's possible to derive credible health index without knowing the loading of a transformer?
I think so, sir. Should I repeat the question?
Yes, please.
Yeah, when we say a particular transformer has served 60 years, we may not get full picture if we do not know its loading pattern through the years. So, do you use any concept that takes this aspect into account?
Yes, that's why age limiting factor was. So even if you even if it looks like it doesn't have a lot of gases, right, in oil, it looks like everything else is pretty good condition. There's only maximum score we can assign to that transformer because it's 65 years old. If we don't know what the loading patterns are, I mean, what they do, they kind of bring you to certain conditions. So yeah, it's very useful information. But indication of where you are really most importantly done through oil quality and DGA testing. And the DGA testing, you look at the rate of change, which are those two things. Ideally, you would have that plus loading, so it gives you an idea to arrive at overall score because it's included in the formula. And if your loading show that you're close to a nameplate rating, or you depending on a percentage of nameplate rating, it would kind of a lower condition of a transformer. It will shorten a useful life. If you don't have that, you don't have that. So you have to build it based on what you have, right? But one thing is you do have to use, regardless whether they have loading or not, you still have to use the age limiter. That's our approach. I don't know if I answered the question. If you don't have something, you can't make it up, right? So you have to deal with what you have, right? Did I answer your
Thank you,
question?
sir.
Did I answer your question? Any more questions?
No, sir, I don't think so. You can continue.
Okay, thank you.
Thank you, sir.
So I'll want to try to get the demo going, okay? Can you see the screen?
Yes, sir.
Okay, so let me set it up first. This is based on actual results from one of the assessment we did for one of the utilities. It's a distribution company. And what you see here, it shows to you condition, distribution, and other things for those asset categories: substation transformers, ped-mounted transformers, pole-mounted transformers, submersible transformers, wall transformers, overhead line switches, ped-mounted switchgear, ped-mounted junction enclosures, and poles. So first of all, you see the table. And the table shows you population in each category. It shows you average health index. It shows you distribution, poor or very poor, etc., for each of the assets. Shows average age and average data availability indicator. Basically, a measure how credible results are. Okay, and the numbers that you see here are the numbers for all the units that you see inside the map. This is what we call soccer field. It shows those numbers in terms of graphs. So for substation transformers, red means very poor. This is poor. Yellow means fair. Green, light green means good, and dark green means very good. It's the same thing. We call soccer field, but it's a very good representation. So you know areas we need to worry about. So those are typical results of asset condition assessment. And one of the things we did here is, well, how do you manipulate the results? How to make it easier to make a decision, what to do and where? So one thing you can do, you can zoom in. You can say, well, I want to see what's in this particular area, what is my distribution, etc. Okay, we have different symbols for different types of assets. So I think if I remember, it's here. It describes which one is what. So different shapes have different assets. But well, that's not important because I want to show you something else here. One thing you can do, you can say, okay, I'm interested in this particular area. So you can make a circle around the area. Okay. And now the numbers in the table and the numbers here are the numbers corresponding to what's in the circle. I don't see them moving very fast. And that's probably because of a delay. Okay. Now, yeah, now they started moving. It takes a little time. Now, the other thing, wait a minute. The other thing you want to do is you might want to look at all the units. Let's say you want to only look at some asset categories. So you can pick, I don't want to look at all of them. I just want to look at wood poles, for example, and associated with wood poles are pole-mounted transformers. Okay. That's it. So now all you see here are only those two asset categories. Again, you can zoom, you can focus on specific areas, and now you see they're all in different conditions. So the red ones are very poor, the green ones are okay. But you might say, well, you know what, I'm really not worried about good ones. I want to know where my bad poles are and where my bad pole top transformers are. So you can go here and you can pick very poor and poor. And now you have a different representation. You only have a sealed table. It has, first of all, only two assets, right? It has only pole-mounted transformers and poles, and it has average health index, and it shows you numbers for each poor and very poor. And you can start zooming in. And in terms of planning what to do, you can have a view like this, where you can actually see your streets, your houses, and you can decide, okay, this is my feeder. Oh, look how many red ones I have. Maybe rather than replacing them individually, and I have also so many poor, why don't I just replace the whole feeder? Why don't I rebuild the whole feeder here? So that kind of facilitates your decisions as to what is the best thing to do. A couple of more things I want to share with you. This is a more detailed view for specific asset categories, and it is actually doing some trending. So let's look at, I don't want to look at transformers because I have special tab for transformers, but let's look at ped-mounted transformers, for example. So it shows that this is where you were at, let's say, 2017. This is where 2018. So it shows you trend, shows the change from one year to another. And what's interesting here is if you look, we have that many very poor, and we replaced them, many of very poor transformers, because now we have fewer. And we had so many poor transformers, we replaced many of them. Where did they go? Well, many of them went into here, because there was the shift from this many very good to very good. And when you put a brand new transformer in, it becomes very good. The last thing I want to show to you is this. This is for stationary transformers. The stationary transformers are, as I said, the most complex and more impactful and important part of the distribution and transmission system, for that matter. So this is a more detailed view of individual transformers. So this transformer here shows what is our all quality score, what is PDF score is, what's DJA score, and see loading. What it means, it's fairly heavily loaded. That's why it's 47. Okay, look at I don't know. Doesn't matter which one. I click on this one. Click on this one. Oh, here is, we have some problems with this transformer, and also what's important. As I said, when you have a poor overall score and you have some issues, it's important to go to component level. So this one tells you exactly which oil quality tests were problematic, and it highlights them in red. So it really helps you as utility asset management, not only to kind of look at the results of asset condition assessment, but visualize the results, play with different areas, assign different things to different jobs, to different projects based on the results. So you're making a step from just having health index results to ability to manipulate those health index results to drive you to what's the right action in each case. I think I'm pretty well done. Just one, I think I'm done with this. I just want to show you one last slide, which explains who asset management engineers are. Hope you will get a little laugh out of this. I always do. Here you go. And this is who we are as asset managers. That concludes my tutorial. We have about 10-15 minutes. I'll be more than happy to answer any questions, guys, you might have.
Hi, thank you for the presentation and the live demo. That was very helpful. I think I got a few insights from all of it. Much of them was a little over my understanding, but specifically talking about the presentation, the demo. My question was, are there who is feeding data into the system? Does it come from the RTUs and the entire workflow that you had shown, or is there any manual interventions where we're feeding data as well?
Very, very good question. This is a demo, so they're not feeding. It's not fed by real data. This is fed by calculated stuff, and script was written to do this. Ideally, if you have an APM, you want to visualize it, because one of the problems with visualizing a demo like this, it becomes very quickly dated. If you don't update it by feeding real data, what you do when you manipulate, it becomes useless. So you're right. In order to make this is a demo, it's not real stuff. So if you really want to do real stuff, you need to feed it with real data. And if data changes, they have to be reflected. This doesn't reflect changes. This is based on assessment done a couple of years ago. Okay.
Right. No, sorry, I wasn't talking specifically about this demo. What I meant was in general, like if the system was implemented at a utility, how much manual intervention is then required?
I'm sorry, I didn't catch the last part. Are you asking how do you update your results?
Yes, I mean, how much manual data do you need to feed into the system, into an APM system to work correctly? Or?
Well, what we find usually, once you do the first assessment, initial assessment, that's the most difficult part. You have to do it, and it's not easy. You have to understand where your data is located, how to extract it, what does it mean, and I don't want to go into what it means, but for example, when you walk around, depending on your inspection practices, you might say okay, not okay, or you might say 1, 2, 3, 4, 5. So it has to be able to interpret it and translate it into your scores. But once you do the first assessment, if you don't have this APM system, which will automatically on a daily basis update your scores, my suggestion would be to review the data at least, or redo the calculation at least once a year. Because, and we've done it, so, and it's not as difficult. The second one, it's not going to cost you as much, and it's less of an effort, because you already know where things are and what you need. One of the benefits also, not only that you update what you have, but it also, you can see the trends. You can compare results of your first survey, let's say, with the second assessment. And you can tell, are you making progress? Are you having fewer units in very poor conditions? Are you addressing the needs or not? Okay. So the short answer is, if you do it manually, I would say at least once a year. If you have IPM, it's not an issue because it will be done daily.
Okay, thank you.
Any more questions?
Any other queries for the speaker?
I'm sorry?
So this is Shashank. I'm requesting the participants if there are any queries.
Okay.
Ladies and gentlemen, any queries for our eminent speaker? Okay.
Yeah, I have a very basic query. If any of the document or intermediate uh, proceedings minutes are open to public, or they are SIGRE publications are all have to be purchased?
I think that from what I know, technical brochures, if you're a SIGRA member, they're free.
Okay.
So if you're a SIGRA member, you go on SIGRA site, you pick the brochure you want, and you can download it in electronic format.
Thank you.
Ladies and gentlemen, this is the last call for asking any queries. Okay. If in case any queries are left, you can also mail them to SIGRE India and we'll get in touch with the speaker.
Right.
So, okay, for now, I think the Q&A session ends here. Now, with the permission of the speaker, we shall be sharing his presentation with all of you. Mr. Yuri, do we have your permission for sharing the presentation?
Yes, I send you the PDF version, so feel free to share with everybody. Yes.
Thanks a lot, sir. So kind of you. So to all the participants, we shall be sharing Mr. Yuri's presentation with all of you. And I would also like to inform all of you that we have already shared the SIGRE membership details and advantages. And I request all of you to consider become a member of SIGRE. So with that, we close the session. Now it is time to thank everybody who has been a part of this program. I would like to convey my special gratitude to the eminent speaker, Mr. Yuri Simberg from Canada, who agreed to our request for taking this tutorial. Thank you so much, Mr. Yuri.
My pleasure.
I would also like to thank Mr. Santanu Sain, representative of SIGRE National Study Committee C1 on Power System Development and Economics and General Manager CSA Limited. Thank you, sir. We are grateful for your time and your gracious presence.
Welcome, sir. Welcome.
Now, with that, I would also like to thank all the participants who joined us for this program. Thank you all for your support, and we wish to organize more such programs for your benefits, and we also hope the same type of support in our future programs also. With that, I thank you all and end the session here. Thank you, everybody. Bye-bye and take care, please.
Bye-bye. Thank you.